let's see if this works. Okay, question mark, question mark. Just start. Let's see. I wonder if this is working. I think it is. I'm not sure. Could be. Let me take a look. You know what? I'm going to assume that it's working, and that one guy who's watching can hit me up in the live chat if it ain't. The hell is wrong with my goddamn YouTube? Apparently everything. Alright, so today, right now, we're gonna go over the everything that you should have to know for the chemistry test, otherwise known as all of the decomposition, synthesis, combustion, double replacement, single replacement, and other reactions. This includes, it's going to include everything I just said. So, first off, we're going to start with the first thing that you should have learned, which was decomposition reactions, right? So there are a couple different kind of decomposition reactions, ranging from very basic, such as NaCl into NaNCl. Easy money, right? Right. Okay, fuck it. Now then, and the other three kinds of decomposition reactions can include the ionic compounds into a metal oxide, so stuff like the metal carbonate, such as calcium carbonate 3 into calcium oxide and carbon dioxide. Now this is going to hold true with the sulfur, with the metal sulfite, which is just going to decompose into the metal oxide and a sulfur dioxide. Okay. Let's see. And then if you want, and then the sulfite decomposition reaction is the same as this one, only it's with sulfur instead of carbon. And the last one of these is going to be the metal hydroxide into a metal oxide and water, like calcium hydroxide decomposing into calcium oxide and water. Now then, hopefully you memorize these from last time, but these are the decomposition reactions, and they require heat to decompose. So when you're doing the free response, don't forget to add this little heat symbol right here whenever you're doing your decomposition reactions. Now then, you gotta be kidding me. Video output low? You go fuck yourself. What the hell is this? Okay, well, rip. Anyway, You can probably watch this later then when it just uploads to the internet. But synthesis reactions are literally just the decomposition reactions reversed. So synthesis reactions are just these two parts going into the one big compound. Now then, there are certain specific examples of both synthesis and decomposition reactions. The special decomp reactions are oxyacids into water and a nonmetallic oxide. So I've got an oxyacid here. This will go into water and the nonmetallic oxide. Now it just splits nice and easy. H2 over here, H2 over here, CO2 over here, CO2 over here. Just splits up pretty easily. So remember, it's an oxyacid, decomposes into a water and a nonmetallic oxide. And I really can't help you much beyond hoping that you can somehow memorize this before whatever test or quiz you may have. Now then, the other three special decomposition reactions are hydrogen peroxide, a hydrated salt, and a metal chlorate. Now then, a hydrated salt just splits up the hydrated salt into the salt and H2O. So hydrated salt, if you'll remember, we did a lab on this. You're going to want to do just the salt times the water, which is pretty basic, and then you're going to want to just split them up. Instead of the dot, it's going to be magnesium sulfate plus 7H2O. Pretty easy. Alright. Now then, somebody asked the question, how do you find out what's being oxidized? So, we'll go over that real fast and we'll finish off decomp reactions. So now, to find out stuff about a redox reaction, which is something where something is being oxidized or reduced, you're going to want to take your reaction, whatever it may be. Let's say it's, let us say we are creating, let's say we're just making magnesium oxide. So we've got Mg plus O2 into 2 MgOS. Now then, both of these on the left are elements, right? Elements have a charge of 0. Okay? Charge of 0. But over here, when they're combined in a compound, now their charges change. So that, in this case, magnesium is +2 and oxygen is -2. Magnesium here has been oxidized. If you remember the acronym oil rig, so oxidation is loss of electrons, which means it's gaining in charge, right? And then reduction is the gain of electrons, meaning it's going to be reduced in charge. This is how you're going to find out whether your reaction is a redox reaction, if something is oxidized or reduced. In this case, the magnesium has been oxidized because it's gained a +2 charge, and an oxygen has been reduced, losing 2 charge. You can find out charge on your periodic table, hopefully by remembering hopefully you can remember from the last period what it was. But the alkali metals have a +1 oxidized state. Alkaline metals +2. Let's see. Now then, going from right to left, halogens have -1. After them, -2 on the oxygen column, and the nitrogen column has a -3. The last two are confusing and generally are not being dealt with in this period. However, elements will have different charges depending on what kind of situation it's in, such as, well, but I can't really think of an example, so you know what? Fuck it. Go back now and finish looking at decomposition reactions. Why is my stream so terrible? Damn it. Oh well. Now then. The last two decomp reactions before I went off to explain redox for some reason. I don't know. Okay, I'm gonna switch colors. I'm bored. Okay. The last two, I believe, were the hydrogen peroxide redox decomposition reaction of 2H2O2 going into 2H2O with an oxygen gas. This is a lot different than you might expect with this, but this is the correct decomposition reaction. Hopefully, you can memorize that shit. Otherwise, you know what? Good luck to you, my dude. Now then, and the last decomposition reaction we're going to go over is the metal chlorate. The metal chlorate into a metal chloride and oxygen gas again. This is different from, say, this is different than the previous carbonate, sulfide, and hydroxide decomposition reactions because the oxygen this time is separate, and the other substance, this being the chloride, combines with the metal. You know what? It doesn't. Alright. Now then, we're gonna go over the synthesis reactions. Oh shit. This is gonna get real complicated. Not at all. Oh, what the hell? That's terrible. That's not even an S. Synthesis reactions. Oh shit, boys, what up? Now, in synthesis reactions, on the side of the metal carbonate, metal sulfite, and metal hydroxide are exactly the same, except they're reversed. That's it. Same thing with the parts into a compound, and all that good. And the oxyacid and non-metallic oxide. Okay, it's all the same, just reverse. Like calcium oxide plus carbon dioxide will go into calcium carbonate. Just like the decomposition reaction was calcium carbonate going into a calcium oxide and carbon dioxide. Right? Same thing's going to happen with the oxy acid. It's going to go from carbonic acid. It's going to go from carbon dioxide and water into the carbonic acid that was decomposed earlier. Now then, the two special synthesis reactions that you're going to need to memorize are going to be is going to be ammonia, NH3 being ammonia, not NH4. This NH3 is ammonia. NH4 is ammonium. This is somewhat tricky for some people, to grasp, and it was pretty tricky for me too. But you just gotta remember, is 3 and is 4. Right? Anyway. The synthesis reaction itself is going to be ammonia and hydrochloric acid into whatever the heck NH4Cl is. Or like ammonium chloride, I believe. And the last synthesis reaction you're going to have to memorize, that's probably going to catch a lot of people out of guard. I don't remember it. But it's going to be acid rain, which is going to be 2 hydrogens or sulfurous acids, aqueous, and oxygen gas to create sulfuric acid. Alright. These are the last 2 synthesis reactions you will have to memorize. That's all you're going to have to memorize off of this one sheet on these 2 precise subjects of decomposition and synthesis reactions. Okay, now then, we're going to start going over single replacement reactions, which are relatively easy to handle, if I can find the notes for it. Here we go. Single replacement reactions is when one metal is replaced by another, more reactive metal. On the periodic table that should come with your quizzes and tests, there should also be a chart detailing the activity series of metals and whether something is more reactive than another. Now then, if you're some far off land that doesn't have this, I'm sure you can look it up on the internet in one place or another to find out what it is. But the basic concepts of single replacement reactions is I've got element A and element BX, and this is going to go into compound BX, and this will go to compound AX plus B. Element A has replaced element B. Whoa. Single replacement. Ooh, spooky. Right? One example of this is this equation of aluminum and iron nitrate going into solid iron and aluminum nitrate. can see that the aluminum has replaced the iron in a single replacement reaction. And if we look at the activity chart that should be provided, aluminum is higher than iron. Aluminum is higher than iron on the activity series. It is a more reactive metal. And now, since we've covered that, we'll move on to how this can affect water. Okay, so in the activity series, and I wish I could get the chart out, but I can't, certain metals will displace hydrogen from both cold water, steam, and acids. Okay, so the most reactive metals, let's say lithium, right? Lithium added to just straight up cold water is going to create lithium hydroxide and hydrogen gas. These are the most reactive of the bunch, such as lithium, rubidium, barium, potassium, and others. Now then, next most reactive will displace hydrogen from steam, and you know, this all builds up. So if you're given steam and lithium, it's still obviously going to create the same product. It builds up on each other. So the next group of elements will displace hydrogen from steam. And one of these is going to be aluminum. Aluminum is going to displace hydrogen a lot, and so will the other metals, to create the metal oxide. Yep. And hydrogen gas. And finally, the last four, cobalt, nickel, tin, and lead, will displace hydrogen only from acids. They're not going to do anything fancy. Let's take cobalt. I have to make up an acid on the spot. Random acid. Say H2SO4. It'll displace that acid to create whatever compound that may be, and hydrogen gas. The equation on the bottom may not be actually accurate, but that should be an accurate representation of what it does in that situation. So that should be everything from single replacement reactions. Now then, we'll move on to double replacement reactions. And this is actually just as simple as single replacement reactions. And don't let anybody fool you on this. Alright? Double replacement reactions are reactions that just have two compounds, right? In this case, we're going to have, we're going to have lead nitrate. So these are two aqueous solutions, lead nitrate and potassium iodide. And all we're going to do is we're going to take the positive part of the compound, or the I believe it's an anion. Don't take my word on this. But it's basically whatever is at the front of the compound. And we're going to switch them. Just switch their positions entirely. So then we'll have potassium nitrate. Make sure you balance. And lead iodide. Now then, you're going to have to figure out these states, the aqueous state for the potassium nitrate, and the solid state for the lead iodide from your solubility rules. There's a lot of them, and you can look them up on the internet, because I, again, cannot show you the chart right here as I would like. However, we can look it up and see that let's say the second rule, depending on what rule set you're following, but one of the rules is going to say that all nitrate compounds are soluble, meaning we'll have, again, an aqueous solution. And we'll look further and we'll see that all iodine compounds are soluble except those of lead, silver, and mercury. And this is definitely one of those situations, and so we have a precipitate. If I could, there we go. We have a precipitate. And what does aqueous means for the potassium nitrate? What it really means is that we put in two solutions of really just lead, nitrate, potassium, and iodine. And iodide ions. They were just all floating within. And what we got out was a solid precipitate of lead iodine and really just still the same ions of potassium and nitrate, because they were both aqueous, and this compound remains aqueous. So really, what we put in were two ions swimming around in solution, and what we got out, they were the same two ions. They weren't combined in any sort of way. And so this entire thing on the bottom is a complete ionic equation, minus the balancing, because I'm being lazy. And so a net ionic equation would be if you took out the spectator ions, the ones that are just still floating around in the solution. If we took those out of the equation, the net ionic equation here would be lead plus iodine, two iodines, is going to equal a lead iodide reaction, or precipitate. And that's everything you're going to need to know about double replacement. Now then, if both products are aqueous, say, and so I guess I lied, it's not everything you need to know yet. If both of them are aqueous, then no reaction has occurred, because you put four ions together, right? So let's say I've got ion plus, and another ion minus, and ion plus, and another ion minus, and all I got was this exact same thing. This was the outcome in the complete ionic equation. Because in the molecular equation, let's say these two combined, but they were both aqueous. So really all that happened was we put four things in, and they just kept on swimming around, doing absolutely nothing. That is a no reaction. You'll mark it down as no reaction. And sometimes when you do a double replacement reaction, you will form water, which is technically a reaction, but it won't be forming a precipitate. So we've got hydrochloric acid and sodium oxide. That's going to form NaCl, which we would know to be soluble, but more importantly, we also have water, which is still a liquid. So this is still technically a reaction. Don't let that fool you. So if they ask you a question about, hey, in this reaction, what's the driving force? And really you see that there wasn't any precipitate being formed, but you know that there's water being formed. So just really the bonding together to create water is the driving force of whatever reaction that may be. And so that really, I hope, I don't think I missed anything, should be the important stuff of a double replacement reaction. Finally, I believe, since we've gone over net ionic and everything, we're going to take a look at combustion reactions. Now, there are two kinds of combustion. Let's switch to red. There are two kinds of combustion reactions. Okay? So, the first combustion reaction is going to be a complete combustion reaction. A combustion reaction that has occurred in an environment of excess, of excess oxygen. So when you write down that arrow, you're going to put above excess O2, and then you'll have products of water and carbon dioxide, and you'll balance it by balancing first the carbons, next the hydrogens, and finally the oxygens. There's 4 oxygens, there's 6 oxygens, so there's 10 oxygens in total. Okay? And this will be a complete combustion reaction. And now the next kind of combustion reaction is going to be an incomplete combustion reaction. So this is a combustion reaction that has occurred in a limited oxygen environment. There's not a lot of oxygen. And so it balances differently because instead of carbon dioxide, there's not a lot of O2, there's not a lot of oxygen, so you'll create carbon monoxide, which is highly poisonous, if you may recall. So here, to work a little bit harder. So first, we try to balance it. We'll do carbons first and hydrogen second, but wait, now I've got 7 oxygens, and I can't balance 7 oxygens. So the trick here is to pick what would you do if you could balance it with a half coefficient, 3.5, and then you simply double all of the coefficients in the reaction, having balanced it out with 8.5. So now you have 7 to 8 and 6. And now this is going to be your incomplete combustion reaction. And this is, I believe, the last reaction you will have to know for whatever chemistry reactions you or any other person may need to encounter in your future chemistry adventures. And so I hope that this was helpful to you. I hope I covered everything. I'm pretty sure I did. I looked through all of my notes and everything. And I hope that you were able to review and or learn. Well, you probably should have learned from a different source if you're learning this from the first time. But I hope this helped you at least review for whatever test or quiz you may be last minute studying for.